Last lecture, we learned that we could represent flow using a potential function if it was irrotational. The flow had no vorticity in it. So now we're going to ask, when does that happen? This is going to take a little while. We're going to go through a complex mathematical derivation, which will show us when essentially we can assume flow will be irrotational, or at least treat it as irrotational. So we're going to consider two-dimensional flow. Keep it simple, and that's going to lead to these two momentum equations that we're familiar with. These are both the Navier-Stokes equations, x and y momentum equations here. And we're going to take the curl of the momentum equation. So that's we're going to take the cross product or the curl of the momentum equations with del. So the curl is when you take del cross whatever. So the curl of the curl of the u vector would be del cross u. We're not doing u, we're doing curl cross these equations. So what we're going to do, del vector, of course, is just d by dx and d by dy. So I'll write those here. That's what we're going to do that's what del is, the gradient there. So we're going to curl that, and in two dimensions, we showed last time that there's only one non-zero component to that with velocity, and that's dv dx minus du dy. So we're going to assume we already know that we're not going to have any other non-zero components with the x, with the u, and the v velocities. So we're just going to take the x derivative of the y momentum equation and the y derivative of the x momentum equation, the u equation. So this is the equation for u, this is the equation for v. We're going to take the x derivative of the y momentum, and then we're going to subtract the y derivative of this one, and that's going to give us some information about the how vorticity moves around and is generated. So that's our goal. So we're going to take the x derivative of the y momentum equation, and we're going to subtract the y derivative of the x momentum equation. And that's going to take a while. So here we go. You can see a lot of terms. So, all right, here we go. X momentum of the x derivative of the y momentum equation. So we have the x derivative of y momentum. So we have d by dx of dv dt, starting out pretty simply there. And then we're going to have to apply the product rule to the next term. So we have d by dx of u dv dx, d by dx of u dv dx. And then we have d by dx of v dv dy. And then we have d by dx of minus 1 over rho dp dy. And then we'll continue here. We'll have nu. We'll assume the nu is constant in space, so we can move the derivative inside the nu. So we have d by dx of d squared v dx squared, and d by dx of d squared v dy squared. So there's our first stab at this, d by dx of the y momentum equation. We're going to try to clean this up, of course. So let's see how that looks. So I'm gonna rearrange this. This is d by dx of dv dt. I can rewrite that as d by dt of dv dx. That doesn't change anything except the order, and it makes it easier for me to see things later. Now I'm going to go ahead and apply the product rule here. So I get du dx times dv dx. And then the second term in that would be u times d by dx of dv dx. And then the second term also I have to do the product rule here. So I've got, first one would be dv dx, and then dv dy. And the second term out of that would be v times d by dx of dv dy. All right, so far so good. The third term, pushing that derivative inside the 1 over rho, so assuming incompressible, of course. We have minus 1 over rho, and then I have d squared p dx dy. And now I'm down to the viscous terms. I have nu, and let's see, how do I want to do anything with this? Not really. I'm going to just keep that the same for now. So d by dx, d squared v dx squared, and d by dx, d squared v dy squared. All right, so there's so far my x, taking the x derivative of the y momentum equation. Now I'm going to take the y derivative of the x momentum equation. So I'm holding on to this. I'll put this off to the side for now. And I'm going to go ahead and take the y derivative of x momentum. So again, I have d by dy of du dt. I'm taking this is the u equation, plus d by dy of u du dx, plus d by dy of v du dy. Then I have minus d by dy 1 over rho dp dx. Come down for my viscous terms. Again, assuming I can put that spatial derivative inside the nu. So I have d by dy d squared u dx squared plus d by dy d squared u dy squared. Again, I will rearrange some terms and clean some stuff up. So I want to rewrite this term as d by dt of du dy. Then, again, I'll apply my product rule here. So first term is du dy du dx. Second term is u d by dy of du dx. And then third term, I have product rule again. So dv dy times du dy. And then second term is v times d by dy of du dy. Coming into the pressure term, minus 1 over rho, d squared p, dy dx. And finally, my viscosity terms, which once again, I'm really not going to do anything with, just leave them kind of the way they are. D by dy, d squared u, dx squared, plus d by dy, d squared u, dy squared. All right, so there's my y derivative of the x momentum equation. So now I'm going to go ahead and subtract this one from this one I had before. So I've rewritten these so we can see them a little better, but this is the x derivative of the y momentum equation. This is the y derivative of the x momentum equation. And now I'm going to subtract this one from that one. So we've got d by dt of dv dx minus d by dt of du dx. Oh, sorry, that would be du dy. Great start. Du dy. Thank you. All right, so now we'd have plus du dx, dv dx, minus du dy, du dx, plus u d by dx, dv dx, minus u d by dy of du dx. And we have plus dv dx, dv dy, minus dv dy, du dy. Try to keep my v's and u's straight here. Plus v d by dx, dv dy, minus v d by dy, du dy. Okay, back on the other side, I've got minus 1 over rho d squared p dx dy plus, because it's a negative, 1 over rho d squared p dy dx. And I've got all my viscosity terms. positive d by dx, d squared v dx squared. I'll just put these together, positive d by dx, d squared v dy squared, and then my two negative terms, negative d by dy, d squared u dx squared, and negative d by dy, d squared u dy squared. All right, so there's my combined formula with one subtracting the other. Right away I can see that these two guys are going to cancel. Second derivative with respect to x and y is the same as second with respect to y and x. Both 1 over rho, opposite sign. So those go away. I've eliminated those terms. The rest I need to try to consolidate somehow. I'm going to observe right away that this term can be rewritten. D by dt of dv dx, sorry, that's an x, good brain work there, minus du dy. So that's nice because that actually looks like the vorticity, and that's what we're really interested in here. And now we've got all these other terms, and we're going to see if we can combine some of those. So let's see, we're going to have, I'm going to combine all the terms that have a u in them, and that gives me d by dx of dv dx minus d by dx of du dy. That's all the terms with u in them. I'm going to then combine all the terms with v in them. V times d by dy of dv dx minus d by dy of du dy. Okay, let's see if we see all that working okay. So that's where my v terms. So I had dv dx. I can move those derivatives, move the dy out, move the dx in. That's allowed. This is just d by dy, no problem there. I've got d by dx with the u terms right there, and then same thing here. I'm going to switch the x derivative operating on the u, move the y derivative out front. Doesn't make any difference which order I do the derivatives, so that's a legal move. All right, so then we don't have the pressure terms anymore because they canceled. Oh wait, we left out some terms. Keep going with the so those terms on the left-hand side. We got more of these terms. We got these du dx's and dv dy. So we've got du dx, try to keep my u's looking like u's, dv dx plus dv dx dv dy minus du dy du dx minus dv dy du dy. All right, so we'll hope that that is right. And then we have no pressure terms. We've just got viscosity terms. So that's going to be nu times, all right, I've got a third derivative here of v with respect to x. So I'm going to write that as d squared dx squared times dv dx. So notice that's still a third derivative of v. I've just pulled two derivatives out front. Second term is going to be d squared by dy squared, same kind of thing, but I've got now dv dx. So I'm going to take two y squareds on this term, and I'm going to pull those out and put the dv dx inside. So again, reversing the order of the integration of the derivatives, but I'm not going to, but that's that. So I've moved that out and that out. And then I'm going to do the negative terms. I have negative d squared by dx squared of du dy. Again, changing the order of the derivatives, but I've got d squared. I'm going to move the du dy here and take the d by dx squared of it. And finally, d by dy squared of also du dy. So that's what I've got for the viscosity terms. All right, so this is all starting to look pretty good to me. It probably doesn't look like much to you yet, but this is looking like vorticity. So this is where we're going to start making some real progress. So in 2 dimensions, we have said that the vorticity only has one non-zero element, and that non-zero element is dv dx minus du dy. which we're seeing appear here. So I can right away write that term is just the time derivative of the vorticity. So that's nice. And then I have plus, well, look at this. This is actually u d by dx of dv dx minus du dy. So that's also going to be the vorticity. So that's sweet. Now, the next term, same thing. I have v times d by dy of dv dx minus du dy. So again, these guys all operating just on the vorticity. The next terms are not so obvious what to do with them. So we'll just leave them alone for now. We'll treat them later. So we've got du dx, dv dx, dv dx, dv dy. Trying to keep my x's and y's and u's and v's straight so I don't screw up later. Minus du dy, that's a u, du dx, and minus dv dy, du dy. Leaving all that alone. On the other side, I have also, though, I've got now, if you look at this, second derivative of dv dx and second derivative of du dy. So I can combine those terms. So I'm going to have second x derivative of dv dx minus du dy. That's this term and this term here. And then I'm going to add that to the second y derivative of this term minus that term. So once again, I have the vorticity. So the vorticity is here, 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 and here. So I can replace all of those with vorticity symbols. And I'm very close to being done now, thank goodness. So we're going to replace all those terms with vorticity. So we've got the time derivative vorticity is equal to, not equal to, is plus u times the x derivative of vorticity plus v times the y derivative of vorticity is equal to this nu times the second derivative, the Laplacian of the second derivatives of vorticity. Oh, I left out these terms again, yeah, dummy. So cross that out for now. Add these other terms in, because I can get rid of them. So du dx, dv dx, dv dx, dv dy, du dy, du dx, dv dy, du dy. That, add those, and then that is all equal to the simple term on the right, nu Laplacian of the vorticity. All right, so all we have to do now to make this really look nice is somehow figure out how to get rid of these. And the way we're going to do that is we're going to recognize that these are actually combinations of things that can be look like the continuity equation. So let's see if we can figure that out. So we're looking for the u dx plus dv dy. That's right here, actually. So I just circled that by accident. So that's great. So I'm going to put this back, d psi dt, eta dt plus u d eta dx, d eta dx plus v d eta dy is equal to this. So I got, what do I got? I got dv dx, here and here, plus dv dx times the u dx plus dv dy. That's this term and this term. And then I subtract, let's see, what do I have in common here? dx, dv dy, du dy. Du dy times du dx plus dv dy. And that's equal to del squared vorticity. All right, so what are these? These right here and right here, those are mass conservation. Those equal 0 for incompressible flow. For incompressible flow, those two terms are equal to 0. So finally, we got rid of everything we wanted to get rid of. So we have the time derivative of the change in vorticity is equal to plus the convection of vorticity, the way vorticity moves around with the flow, is equal to this simple Laplacian dependent on viscosity of vorticity. So it looks almost exactly like the x and y momentum equations in 2 dimensions. So this is 2 dimensions, and that's an incompressible flow. So that's what we've assumed so far. So 2D incompressible. And what is this equation telling us, which is really the whole point of this analysis? The only real thing we're trying to get away from this, you can use this to calculate vorticity, and some people do that. If you're interested in how vorticity is moving and it can affect flow fields, then this is a useful vorticity transport equation. But that's not really our interest in it. That's beyond the scope of this class. For our class, all we really want to know is, does an irrotational flow remain irrotational? So what this is telling us is that if vorticity is 0 in the flow, if it's 0 in the flow everywhere, then it can't be generated except by viscous effects. So if you have viscosity, if you have a flow that has no vorticity in it, and you put like a solid surface in it, then viscous effects can start to generate a non-zero here, and that can generate vorticity, an increase in vorticity over time. So if you have viscosity, you can change the vorticity in the flow. But if you have no viscosity, if this term is gone and all you have are these terms, if you put a solid in the flow now, well, U and V at the solid interface go to 0, so they can't create any vorticity. So no vorticity can be created if there is no vorticity in the flow and if there is no viscosity. So irrotational flow remains irrotational if it is inviscid. So inviscid means no viscosity. So if it's an inviscid flow, 2D or 3D even, actually this applies to 3D as well. If it's an incompressible flow and it has no vorticity in it and there's no viscosity, which means it can be treated as inviscid, then there will be no viscosity in there'll be no vorticity in the flow at all. The total flow will remain irrotational. And so what that means is that we can use potential flow theory, because we learned that we could use potential flow in the potential function if we had irrotational flow. Now we know that if we have irrotational flow at some point, we won't have any rotational flow as long as the flow is inviscid. So if we have inviscid irrotational flow, we can definitely use the potential function.